Sorry.
Okay, all right.
So,
Anyway, so the whole point is that, okay, the application wants a lot of things, so high bandwidth, low latency, and they want to do a lot of jobs, spending a lot of CPU cycles. And to support those applications, networks or transport, they are doing a lot of things to support those applications. So on the other hand, it is also clear that data center applications, they also need end-to-end encryption. Okay? The reason is data center infrastructure is essentially multi-tenancy. So they have a lot of tenants by letting out virtual machines or other even the serverless functions or other form of any services to different tenants. Also, so data center network infrastructures are essentially multi-vendor in terms of hardware equipment or software network components. For example, like maybe even the hyperscalers, they don't build every component of the hardware from themselves, but they source, for example, cables, interface modules, switch from many other the vendors. And also some part of the networks are managed by third party, right? For example, like a Silim bought by Cisco, and they are like providing some in-network observability services to the tenant or operators. So data center networks are really, really key, kind of mixed vendors, multi-tenancy. So careful application or tenants or users, they really want their data to be encrypted while their data is in transit to the network. So here is where challenges come from. As I said, the modern transport protocol, like in the layer of the TCP or RDMA or those parts, are very, very complex. They have very, very strict requirements. For example, they no longer use traditional TCP. They may use kind of some rocky kind of things or even receiver-driven congestion control. They want to send application data in the very fast round trip time without doing connection handshake. And also, in terms of abstraction, modern application want the message, when they send some messages to the other side of the network, they want to get the message boundaries are preserved. This thing can't be achieved by TCP. And also hardware fraud is quite essential because application want not only to drive very fast the network fabric, but also the role of transport. Definitely the networking stack can't waste all the CPU cycles. They have to leave as many CPU cycles as possible to the applications. And also it is increasingly clear that the pure end-to-end congestion control is not sufficient to meet high throughput and low latency requirement of the applications. And so, so some network compute usually means that some fine-grained load balancing. Okay, so traditional load balancing is per connection. So if you have, say, 100 TCP connection, then the TCP connection 1 to 10 goes to this path. TCP connection to 10 to 20 go to this path. But this kind of per connection basis load balancing was the traditional way. But it is increasingly clear that lot of applications send multiple messages within the connection. Okay, this is important for a number of reasons. But in such a cases, like actually the network want to do per message. Okay, so can be within the same connection, not per connection. Load balancing or congestion signaling or other form of some resource allocation, bandwidth allocation kind of thing. Uh, they need that again for high throughput and low latency. So question is, can we add security features to the existing kind of the transport protocols without sacrificing those important properties? This is those are the questions whether the research I'm introducing solved. Right. So here is the design space of say the transport level encryption. So we can divide some relevant existing work into two pieces. And one is about transport level encryption, and the other is message-based transport. As I said, nowadays it is very the kind of agreed by the community that the data center need message-based transport. Right. Let's take a look at some problem with existing, say, encrypted transport protocol, making some exception, reading it later. So the transport level encryptions are based on TCP and QUIC. They have some common problem caused by byte-stream abstractions, or it is like the headline blocking. So think about the case that application sent two messages, and first one, yellow one, consists of three packets. And the second message, logically independent message, consists of just a single packet, tiny, tiny packet. And think about that the third packet of the first message is lost. Okay. So what happens with TCP or QUIC or any byte stream abstraction transport is, so application get, yeah, those first two packets of that first message is fine. They just want to be delivered to the application. But before the logically independent second message delivered to the application, there's a lost packet uh, that constitutes the final piece of the first packet, first message, has to be retransmitted and then delivered to the application. Then the second message finally can be delivered to the application. Okay? So this delays the application level delivery of this, say, potentially very important small messages. And this is how headline blocking happens with packets. Another example is the headline blocking caused by CPU hotspot. So think about the same scenarios that even without packet loss, say the two messages, say the large message and small one behind that arrive in the, say, the bottom of the network stack. And if some, say, imagine that this is the connection, and then if some so basically the modern network interface, they load balance the network data based on the connection. So all the messages, in case of TCP or QUIC, so the messages in the same connections are processed by the same CPU core to avoid reordering. So if the moving or processing those, say, part large message takes time on this CPU core, then this is a last, say, very tiny message just arriving later. They're going to be delayed. So the headline blocking in case of TCP or QUIC, there's a mainstream transport today in the internet. They call the headline blocking in both the packet loss and CPU core. Now then, let's take a look at some of the existing, say, data center transport called Falcon or the AWS SRD. And they're also pushing some data center transport. So the Falcon is based on the Google and AWS SRD from AWS. But they are either like a connection oriented, which is a case of the Falcon, and which has the same problem with the TCP or UDP, TCP or QUIC, and SRD is like AWS's RDMA-like transport, but they do support an ordered delivery, but that is the granularity is a packet. So they can deliver an ordered packet to the application, but they don't guarantee to provide abstraction of an ordered message delivery to the application, which means that in the maximum size of the messages that application can send and receive is actually single packet size. Okay. So it's not very general. So we have to add an extra software layer, on top of that if we want to do real the message or the message based the abstraction. So now we have kind of middle ground. So we reviewed that existing encrypted transport protocols are not enough to support modern data center requirement. So the middle ground we're going to start from going to be like an encrypted message-based transport that is achieved by Homer MVP or MTP, those relatively recent transport protocols. So the Homer is probably the most practical one because it is actively developed in Linux kernel, and its design is also general enough to transform to other protocols like NDP and probably TCP or some other data center transport. So MTP is very similar to HOMA, but the nice thing about let's say the hotnet paper and in the reference is they introduce some nice list of the in-network compute. So they using simulation analysis, they argue the need for fine-grained message per message load balancing, multipath selection, and conditional signaling. Also data mutation like some in-network data caching. So in both home and MTP, I assume that you know some basic packet format of TCP, like the eTCP packet had some sequence number which shows the byte offset within the entire connection. But in the message-based transport, the packet format has some the message ID and message length, which are embedded, same values are embedded in the every packet in the same message, but every message has the message offset in each of the packet. In this way, um, this transport level header can represent arbitrary part of the message, with arbitrary part of the arbitrary offset within the same message. Okay. So the why MTP argues that, or the why that this format, packet format can achieve in network computing is that, so the routers are switches, they can buffer entire message in the bounded resource allocation, which means that in case of TCP, it is impossible to find the application level message boundaries within the connection, but in message-based transport, the router switch just first find some new message ID and the length, then it can just keep that the state of that message until this is the message offset fills hold the length. So here is our design of SDP as SDP. Sorry, this is the name it. Just spell miss of SDP. We call it SDP. And the overview of SDP is, it is like, again, it's a transport level encryption for data center networks. And it is, again, it is important to support message-based transport abstractions. So for in-network computing support and other purposes. So the SDP allows even data mutation if some key is shared with some switches or middle box entities. And we can use opportunistic NIC offload. Okay? And we don't need, say, the new, say, the vendor specific or hardware, and we can use a commodity NVIDIA connected 6 or 7 NICs, and the same NIC offloading architecture used by other NICs, like Microsoft, the fungible, and some of the natural norm NICs as well. And SDP is transport protocol number agnostic, so we don't have to use TCP protocol number, so which makes some the coexistence with existing traffic with TCP or UDP in data center. It makes it very, very easy because the network management or some observability software, they do not confuse SDP traffic with some other traffic. And we can do optionally we can also do some zero RTT, some key handshake to I omit this from this talk. So current implementation of SDP is say the 2.8K the lines of code change in home Linux in the Linux kernel, and some 300 lines of change in the NVIDIA the NIC driver, and currently worked in 2 versions of Linux kernels. So the first question actually we faced is whether to do, say, the new transport protocol with encryption. Can we do that using existing NIC without redeveloping the hardware? So we looked at some two mainstream, say two existing some of the TLS offloading architecture, and then so the first one I take a look, it just tells you the Terminator 6 NIC. This is kind of old. But we found that this offload is really, really bad. And we saw some other articles that they are even criticized because it is not good even for TCP because it strips even all the TCP options like SAC or multipath TCP or even window scaling, and it's unfavored by the operators. And based on that, the NVIDIA Mellanox, they developed another architecture of TLS offload, which is called autonomous offload. And that is quite mainstream today, and interface to the software is well documented in Linux kernel documentation. And which means that so it is kind of some hardware software kind of some cooperative the offload architecture, so that we can guess the hardware architecture, the hardware offloading architecture used by specific NIC by looking at device driver. So we did some check, and it's likely that the Microsoft Fungible or Netomnics, and they do the quite same architecture. So we believe this mainstream TLS offload architecture is quite general. So we did some tests by giving definitely their TLS, therefore TLS, so assumes TCP, but we gave some packet, TLS packet, but whose network layer header doesn't indicate TCP, and actually it worked. So we spoke to the NVIDIA's the person who developed this, and yeah, this is not gonna be the bug and gonna be kept. So then we found that, okay, this is a good opportunity to start, say, to design protocol agnostic the secure data center transport while using existing hardware offload. So the behavior we expected like this. So usually, so the TSO means TCP segmentation fraud. So the TCP stack usually doesn't create some the doesn't really create a packets, but the stack creates some larger packet than the network MTU size. So then the NIC split that packet into smaller MTU size packet. Okay. So what we tested is whether TLS offload worked together with TCP segmentation offload, and it worked. So the first challenge was in designing SDP was we really wanted to support any size and ordered authentication message delivery to the application. Okay. So the problem is the application message, okay, it can be arbitrary size, which means that it can fit into a single packet, but it can fit into a single TSO segment, or it may consist of that even multiple TSO segment. Okay, so here is how it works and how the message assembly and reassembly works with SDP. And the sender side, so sender side SDP stack creates, say, in this example, like because of message size, it creates two TSO segments. So each of the segments preceded by IP header, again, which doesn't indicate TCP, and then kind of fake TCP header and TLS header and authentication tag for each of the TSO segment. And it also embeds some of the framing headers in the middle of the payload. This is required, which those framing headers are required on reassembly, and I'm going to show them next. So in the end, by the NIC, again, commodity one. So the packet, so those two TSO segments are split into 6 actual packets, and those are the indicated parts are encrypted, and each of the yellow, the embraced part contains a single TLS record header. So then, so the receiver using some IP-ID field, which is also generated by the NIC, it's first reassemble those TSO segment, okay, before reassembling it into the message. We can do it using IP-ID, which also generated by incrementing a value for every packet by the NIC. And then those TSO segments are going to be those TSO segments are going to be decrypted, okay, using record sequence number and shared key or negotiated key beforehand, and it finally reassembles application level message. So it may look simple, but it actually is quite challenging within the operating system because SDP needs to support message level parallelism. So granularity of the parallelism, okay, within TCP, it's a very straightforward, inefficient but very straightforward. Because in case of TCP, it is a connection-based protocol. So whatever the retransmission, acknowledgement, or new data transmission, everything is serialized over some single socket lock. So when application send those three messages in a single TCP connection, it's just the serialized. So it goes even down to the NIC and just send out. So no problem. But in case of SDP, so those messages can be scheduled and sent by the different CPU core without holding this centralized lock. So if we badly design SDP, like if we map, say, in case of TCP, say they have a record sequence number, TLS record sequence number 012, but in case of SDP, it may have like sequence, if we assign the same logic with TCP to each of the message, then those record sequence number get out of order. Then in one unfortunate result, receiver decrypt record sequence number 2, which arrived earlier, but receiver expect record sequence number 0, so decryption fails. And in another unfortunate case, receiver waits for the record sequence number 0, and even though other record sequence number or green and yellow one already have received, but it causes headline blocking. So what we do ultimately is like we assign some separate record sequence number space for each of the application level message within the same kind of TLS, say kind of virtual connection or authenticated session. So in the wire, it looks like, so the record sequence number always starts from 0 for each of the message. So in the wire or the cable, it looks like this. Okay. Yeah, so the assigning some separate record sequence number per message, okay, this is straightforward, but it works in terms of, say, the avoiding headline blocking or decryption failure. But the problem is now replay attacks. So replay attacks mean that sending same message or packet twice to the receiver, say by sniffing packet and send it again. Then there may be some, for example, like some receivers which need exact one semantics or any or when receiver expects the same message arrives only once. In that case, it is definitely it's harmful, and this also breaches some of the threat model which provided by original TLS and TLS over TCP. So in the end, what we do is so TCP case, the record sequence number is unique, it's fine. But in our case, we just each of the message has unique ID basically, but we strictly limit the recycling of the message ID just once in each of the authentications or authenticated session, which means that it rarely happens because currently it is 64-bit. But if the message ID run out, so sender and receiver must regenerate the keys and by 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 updating the session keys. So also some similar problem like some of the message level parallelism even within the same, say, the source destination tuple or endpoint. The same problem happens also in case of NIC offloading, because the NIC also expect some of the in sequence record sequence number. So if we generate out of the order record sequence number to even the local NIC at the sender side, then the NIC also confuses and generates some wrong kind of authentication tag for the TLS record sequence. So this is a logical view that what happens in case of TCP. So how TCP works is maybe CPU core 1 sends some new packet used in the system call context, but then when it receives ACK, Then this act gonna be processed by another CPU called interrupt context, and then it pushes some the next available data, okay, which was weighted to get more, say, window space or something. Okay, but those are anyway serialized, so no problem. But in case of message-driven transport, they can be sent in parallel because those belong to the different messages. So we have to avoid the nick to get confused, and having two separate record sequence number space per message helps supporting this the message level parallelism behavior. So here is some of our some basic performance. This is just the most basic latency, simply measuring round trip time of the single remote procedure calls and by changing the size. So HTTP is faster than say KTLS, which is TCP-based counterpart by say 13 to 32% when we use a TLS offload, and 10 to 35% when we do not use TLS offload. So my point is that the Homer, which is like which we extend to implement HTTP, is faster than TCP by 5 to 35%, which means that the most important performance metric for us is it doesn't kill some performance benefit of Homer over TCP. Okay? So it is quite a good number that we achieve outperformed KTLS by 13 to 32% or 10 to 35%. And we ported that HTTP to Redis. Redis is kind of widely used key value stores, and then we measure the throughput using the YCSV workload A and B, update heavy or read only. And yeah, we confirmed that HTTP outperforms by 5 to 30% with TLS offload and 8 to 17% without TLS offload. So here is a summary about this talk. Yeah, so it is clear that we need security or encryption in data center networks because data center networks are multi-tenancy, and it comes with the built by or congestion signaling or other hardware and software. But it is quite challenging. They need that again for high throughput and low latency. Load balancing or congestion signaling or other form of some resource allocation, bandwidth allocation kind of thing. They need that again for high throughput and low latency. So question is, can we add security features to the existing kind of the transport protocols without sacrificing those important properties? This is those are the questions whether the research I'm introducing solved. Right. So here is the design space of say the transport level encryption. So we can divide some relevant existing work into two pieces. And one is about transport level encryption, and the other is message-based transport. As I said, nowadays it is very the kind of agreed by the community that the data center needs message-based transport. Right. Let's take a look at some problem with existing the encrypted transport protocol, making some exception, reading it later. So used by the host operating system as well, I guess. Yeah, I'm curious about that part.
Okay, thank you, Michio. Yeah, and then further questions? Okay, yeah.
Thank you for an interesting talk. I actually wanted to ask you about something that I don't know how much will security in data center networks help with. A lot of the attacks in data centers are actually side channel attacks. So there are a few papers where people basically showed, well, there are all the Rowhammer attacks, there are all of the there's deep theft.
Sorry, type of what?
Deep theft, where people actually can fingerprint workloads and basically steal from there. Did you have any insights into basically how much are that attacks inside the data center network on the network level versus how much is it like?
Okay, so yeah, it's a pretty good question. Currently, our goal is providing some same threat model with TLS over TCP, but definitely it's a protection against a fingerprinting kind of thing or side channel kind of thing. We need say more stronger strategy. Like for example, like usually fingerprinting works in a way like the prediction path, the running over the patterns of the packet or the size of the packet, etc., etc. So those things are, I mean, they have to be changed. And actually, in a separate project, we are working on like changing some packet timing or some adding padding or something to prevent from the side channel based information leakage. But yeah, it's a completely kind of, yeah, we need separate strategy and we have to work on for this kind of thing on say packet scheduler kind of things. Yeah.
So, a second question very quickly is I'm aware that there is now some work that has been looking at IDS, intrusion detection systems using transformer models. There are a couple of papers.
Sorry, what snap? So,
intrusion detection systems where
IDS.
they monitor the network and they claim that they can actually characterize encrypted packets. There are a bunch of papers that came out in WWW and a few other venues. So do you think that this is a challenge and for future networking in the data centers?
So yeah, in that sense, so our assumption is the same with the TCP and TLS. So for example, we have actually whether, for example, if intrusion detection systems, it keep getting the packet and keep say encrypted packet and they try to analyze it, right? So it depends on how the key has been set up, right? So if the key has been exchanged over say maybe some strong fault secrecy, then it's gonna be safe. But if it was not, it's not. So it's the same thing with analyzing some of the TCP TLS packet.
Hello, thanks, Michio. My question was exactly about the key exchange.
Yeah.
So first of all, is there a key exchange for the encryption? And if there is it message based?
So so the key exchange protocol is simply based on KTLS. KTLS, how it works is like basically the application just exchange the message in whatever the way, then it register the exchange or then establish the key into the socket. Then the rest of the packet is encrypted by the kernel. Okay, this is how KTLS works. So we borrow the same idea, like we decouple this is the data message exchange from the key exchange, and key exchange can be done in whatever the way, which means that yeah, it can be done even in another transport, even RDMA or even over TCP or something. But then the point is that the SDP gonna be just activated on the socket by giving the key on that. So yeah. So but we are also working on some the problem with key exchange. Yeah, once the keys exchange, we can reuse it for the not forever, but for a while we can reuse it. That is fine, but still, because like the replay attack protection or some other reason, for example, and always in data center, some new client comes, they leave, server appears, they disappear. So we still need quite often key exchange. So we are also working on some way to reduce some key exchange time, because that is quite actually expensive. And so yeah, also now the people want post quantum security kind of thing. So yeah, in separately bit, but we are working on some fast key exchange on that here.
So message-based protocols are generally connectionless. So you
it's a generally connectionless, yes, but we have to keep the soft session.
Okay.
In terms of secure, authentication.
Thank you. Okay.
Yeah, thank you for the talk. So in the data center networks, I think it always have multiple tunnelings.
Transport what, sorry?
The tunneling of different protocol. For example, the IP tunneling or.
Oh, I mean tunneling, okay.
Yeah. So how do you think is it tunneling matters? For
No,
you?
so actually, no, this is not even encapsulation. It's actually naturally fit in the exact same layer with TCP or UDP. So it's completely agnostic with how the packet going to be encapsulated in some other SIM layer protocol between the network and the transport layer. For example, like it really doesn't matter whether, for example, maybe this can be encapsulated by IP/IP or VXLAN or Geneva, whatever.
Yeah.
It's a completely agnostic because their job is basically addressing and the routing. Okay, so what we care is a transport, which is more about congestion control kind of thing. So, yeah. So, yeah. In short, it's a completely agnostic to the tunneling protocols.
Yeah, I think as you said, for some like the Geneva tunneling or the GRE tunneling, they also have its own encryption.
So, okay, so the point is that those encryption, yeah, they're kind of, I don't know how much it is used, but yes, it exists. But our point of view is, I think those are problematic, especially to support in-network compute. So if we use IPsec or those kind of tunneling protocol-based the encapsulation, then we can still do kind of IP address-based, some or connection-based, some in network processing, again, like making some path routing decision or something. But well, we can't do that message based because usually it's a network layer or say layer 3.5 header doesn't have any indication about message application message boundary. Okay, so actually another important goal of SDP is we export this message ID and message offset part to in plain text, but the rest is encrypted. That is the major difference from the QUIC or other encrypted data center transport protocols.
Thank you. Thank you.
Okay, thank you. Any further questions? Okay, thank you, Mitchell. Yeah,
Thank you
for
very much.
your fantastic presentation. Yeah, we will have a 15 minutes break and we will back for the panel, and it's the most interesting part, I think.